It's going to blow
Some
our socks
ridiculous
off.
stuff.
But I'm thinking back to when Hubble was commissioned when I was a kid,
Yeah.
and right through to today, we're getting stunning images. It doesn't end. It doesn't stop. You don't just see one stunning image and then say, "Oh, well, that was pretty good."
What's up, you scholars of enlightenment? Dr. Sam Gregson here again. I hope you've had a wonderful day on this fantastic, historic, milestone day for science. Today and yesterday, NASA released its first full-colour images and spectroscopic data from the James Webb Space Telescope. And I think it's fair to say that scientists around the world are pretty excited about them. The release represents the first wave of full-colour scientific images and spectra the observatory has gathered, and the official beginning of Webb's general science operations. Today, we will be discussing those images with Professor Paul Byrne. Professor Byrne is a professor of Earth and planetary science at Washington University, where his research focuses on comparative planetary geology. Please enjoy this fascinating conversation. So, Paul, NASA has finally released the first 5 images from James Webb Space Telescope. Before we get into them, what's your general reaction to the live stream and the images that we saw today?
I think the images are beautiful. They're just absolutely stunning. They show, if you knew nothing about science, you didn't care about cosmology, they're just absolutely terrifically beautiful images. Hats off to the entire force behind the JWST project, but also the folks who took those images, ran them through filters, and prepared them for public release. They picked the best ones, the ones that are really going to grab people's attention. And also, it did a really nice job of showcasing the capabilities of the telescope itself. So overall, it was terrific. The live stream kind of sucked.
I wasn't going to say anything about that.
Yeah, the live stream itself, logistically, but hey, at least we can see those issues with the actual telescope itself.
Yeah.
So overall, it was a terrific experience, and to see those images with everybody else was really great. And to be on Twitter and see people's first raw reactions. That was really cool.
It felt a little like all of the they got away with all of the tech issues on the telescope, and it somehow got loaded onto the live stream today.
They were cursed the live stream.
That's how.
But let's take a minute to just recognize how much work it went into making the telescope work.
Yeah.
And not having any part of it break, right? Because this thing is way out there in the dark. We can't go and fix it. We don't yet have the technology to send humans to fix it like we could for Hubble, which is in low Earth orbit. So, I had nothing to do with the mission, and yet I was nervous.
Yeah.
So I can't imagine how the folks at the Space Telescope Science Institute, or really anyone involved in Goddard, NASA, Northrop Grumman, you name it, felt when this thing was being deployed. So.
I agree with you. It did feel like a tech demo, though, didn't it? It did feel like they've got these 4 major sort of four major science themes for JWST, looking at the evolution interaction of galaxies, looking out as far as we can into the past, looking at stellar birth and death, and looking at exoplanets. And they really managed to get all of those into the images that we saw today, which was really nice to see that essentially JWST is open for science business on all of these fronts.
Absolutely. And, this thing this was not just sort of a one-off event. We found out earlier, about an hour ago, that we're going to get images of Jupiter and other solar system targets on Thursday.
Oh, wow.
Which were used in the commissioning and the calibration of the telescope. And as far as I know, the first science from the community will be performed next week. Now that JWST has been calibrated, verified that it's in good working order, the final bit of the commissioning was done yesterday. It's now open for business, and that business will be performed by planetary astronomers, by cosmologists, you name it, who have applied for or will apply for time on the telescope, on the spacecraft, competitively, and then they'll be able to go and decide, well, I'm going to do this project, I'm going to go. And Webb will look at things in the solar system as well, right? It's going to look at Jupiter, it's going to look at Uranus, Neptune. Uranus, of course, target for a recent flagship recommendation from Planetary Decadal. It's going to look into the deep beginnings of the universe, like its deep field images. We're going to look and see how galaxies form and how stars die and all kinds of things. But it's going to start. So in other words, the images we've seen just today, this is like a one-off thing, and now we go back to our normal programming. this is setting the stage for what's coming in the years and decades ahead.
Yeah, amazing stuff. And all of these 5 images that we saw today were of targets that we previously knew of, right? Which I actually really liked, because we saw new stuff in the background of these images, but it also showed the improvements of JWST relative to previous missions.
Oh yeah,
We also got that,
and some of those improvements are really noticeable, right? So you can see, for example, right, so there's the Carina Nebula, which is an area where basically you have.
Let's start with that then, the Carina Nebula.
Yeah, this is my personal favorite.
Okay.
And right, so this is one we have images of it before.
Yeah.
And we have images of it in different wavelengths.
Yeah.
And Hubble has been, like this image, right? Hubble has been our eyes into the universe. But then you get the images from Webb, and suddenly what might look like a fairly thick, opaque wall of dust, you realize is much more tenuous. It's got much more structure. You see way more smaller stars, smaller features. You see these cavities, these bubbles of air. Oh, well, air is the wrong word. You see cavities where dust is relatively absent because it's either blown away by stellar wind or it's been accreted into a young star, because this is essentially a stellar nursery.
Yeah.
But the detail here, the structure, the kind of tenuous, and by the way, it might look a bit like if you ever swirled, milk into tea, and you kind of get these kind of complicated, like in a manner of speaking, some of the same physics are at play here. Scale is much, much larger, both temporally and spatially. But here you have basically clouds of dust that are moving, and they're being pushed away by stars, and they're being pulled in by stars, and they're being gravitationally perturbed. But you get this sort of mixing of all this material. We think of space as empty, and it is. But if you go near places where stars are born, for example, it's full of stuff.
Yeah. I've got to say, this was my favorite as well. It's just so visually stunning and just.
They were so right to keep this to last. This was the last of the 5 they released, and it's just aesthetically. Again, even if you didn't really care otherwise for how planets form or how planetary systems come to be or something, just looking at that image, it's just stunning.
And as you said, this is a really nice sort of example of how well it can see through gas and dust, right? So we have had pictures from Hubble where we look in the infrared to see through this gas and dust that's there. But usually when we look more in the visible spectrum, we get these beautiful pictures. So these are are they the Mystic Mountains of the Carina Nebula?
Right.
But you can't see much of what's going on. The stars inside being born. You go to infrared with JWST and suddenly it's just like opening the curtains.
It's chock full of stars. Exactly it. Yeah. It's chock full of stars. And so that even from a very kind of practical scientific perspective, this is valuable information to understand the rate of stellar formation.
Yeah.
How frequently do stars get right. This is really important stuff we didn't know before. But when I can't but keep coming back to the fundamental point that it's just beautiful.
Yeah.
It's just I'd happily have that as a desktop picture and I'd print it up and put on my wall. Even if you didn't know what it was.
I've had the Hubble Deep Field for like 15 years or something, and now they're all going to get replaced, which is kind of nice.
You step it up more than one notch. Exactly.
Exactly. After that, one that I thought you might be particularly interested in was, as a planetary scientist, was WASP 96b. So this is a huge exoplanet, which is 1,150 light years from Earth, orbits its star once every 3.4 days, and it's half the mass of Jupiter, discovered in 2014. Now, they managed to do both the transit and the spectrum of this exoplanet. Do you want to tell us a little bit about that?
Yeah, okay. So basically, one of the ways we have of detecting exoplanets in the first place is this method we call transit photometry, right? And the concept is really simple, right? So if you look at the graph, you have starlight at some amount of a level. If you look at the picture above it, you can see that there's the moon, or usually it's a planet, and the way they've drawn it here is that they have sort of the planet is a sort of the darker disk, and there's like a lighter gray ring around it. That thing is orbiting the planet now, or the sun. For this to work, of course, it has to be aligned as close to as possible, edge on for us, which means there are an untold number of systems that are not edge on that have worlds that we can't detect with this method. So it's our detection methods still heavily biases towards particular kinds of things.
Yeah.
But anyway, so the point is this thing's moving, and as it moves across the face of its own sun, its star, the light from that star dims, and it dims down to a bit, and then as that planet transits or moves across the face of that star, the amount of light that's being blocked is about the same. And then as it sort of moves away towards the other edge of the star, then light comes back up again. Right? So that dip, and the dip in and of itself isn't all that important. What's important is, do you see it recurring regularly? Is it something you can systematically see again and again? Does the dip change how much it dips? It turns out actually that you can unpack a lot from this.
Yeah.
But what's really cool, so first off, this is, we knew Webb would be able to do this. Now we know that we have these data and they're nice and tight, they're sharp data. But what's really cool is that kind of diffuse gray ring around those things, that's the atmosphere.
Yeah.
And for a very, very short period of time, there is starlight shining through the atmosphere of that planet. And Webb can detect that light and it can look at, and we get what's called a transmission spectrum. And what we see is, you can basically look at the abundance or lack thereof of key things, key elements, key molecules in the atmosphere as a function of wavelength of light, which is the wavelength range over which the instrument operates. And in doing so, we can work out what's in the clouds of that exoplanet.
It's
and so we can say what it's made of. Because from that, then you have all this information you can use as well. How, for example, we know there's water clouds in this. In fact, there's 4 discrete kind of these little rises or crests where you have this. And we've got model data, but there's other things the model will miss as a function of not knowing how to parameterize it, or how you can make the model realistic. That these things, already there are discussions on Twitter about making sense of the WST-96b spectrum and its atmospheric composition. There had been a view that because of something to do with how sodium is perceived by other telescopes, that this world had no clouds. And now, this morning, we're seeing that it's probably quite cloudy, with water-rich clouds. Now, this is a world, you said, it's half the mass of Jupiter.
So we've got the weather on an exoplanet which is 1,150 light years away.
And we can tell a huge amount. Now, to be clear, this thing is about 150 times the mass of Earth. It is not an Earth-like world. It's not a super Earth. It's not a rocky planet. So it's not going to have weather on rock underneath it. It'll be closer to something like Saturn. But the fact that we can now say what the weather is like on an exoplanet 1,150 light years away.
Absolutely stunning stuff. And the amazing thing about this as well, if we look at the sort of previous data, this gets out to like 2.8 microns, something like that. Yeah. If you look at the previous spectra that we had, I think they only go out to about 1.8.
Yeah.
So we can see the extension of that spectrum and driving down those errors and extending to see new features and extending that spectrum as well.
And understanding all the chemistry that you learn from looking at those profiles then feeds into models of, well, how did it get there? What does that mean for the planet's evolution? All kinds of questions that you get from there. I mean, these data are just astonishingly good. And also you'll notice that, the error bars on these things, particularly back to the Webb image, they're pretty tight. And the integration time, the time Webb was spent looking at this planet wasn't all that long.
Yeah.
The error bars get bigger towards the right, but you can see these are pretty tightly clustered data. The quality of the data is really impressive.
I think that's actually a really good general point to make with this. I think for the deep field, which we'll chat about in a second, they made it in a day, and I think Jane Rigby made a point in the stream of saying, we basically did this before breakfast.
That's not what we're used to.
That's not what with Hubble. Right. We're talking about days and longer than that. If you want 11 days, for example, in integrated time, you've got to wait for it to go round the Earth, which might be 22
Right, exactly.
days.
It could be exactly. So, one of the deep field images are 22 days of observations, but it was 50 days of on-orbit operations because of also there's a queue, and other folks are kind of taking the telescope on their time and so doing their stuff. Whereas to be able to point something into the deep sky and just like open the shutter, essentially, figuratively, and let it sit there for a few hours to integrate it onto the sensor is amazing. We're not used to that.
So let's talk about the deep field image then. While we're talking about these integration times. So we also got a picture of I don't know if you'll allow me to say SMACS. Is SMACS allowed?
I haven't heard.
Or do I have to say SMAC?
I haven't heard people say it's not SMACS. So I think we're fine.
Okay, good. We'll go with SMACS then. So do you want to tell people this? So here's an image of SMACS from the Hubble Space Telescope. Right. And then we've got the beautiful upgrade from
superlative picture from
JWST.
So the reason SMACS is important is because this is an area where we happen to know that there are very large gravitational masses that lend themselves to distorting space-time, which basically acts as essentially a lens. It bends the nature of space so much, it's so heavy, that it actually allows us to see stuff that's behind and really far away. Now, that's one of the benefits of that's partly why they took this particular part of the sky. We knew what this part of the sky looked like. We didn't know it looked like.
We already knew it was a gravitational lens, so
we knew it was a place where you could get lensing. Absolutely.
They could flex a little bit and say, not only can we push out further with our longer wavelength and our bigger mirror, we can also push out further if we also stick a lens in front as well.
Exactly. And so, for example, you can see that there are these kind of strung out, like linear looking things that occur in a few places there. And there's a few kind of across the way. Yeah. And it turns out that's all the same galaxy.
Yeah.
And one of the ways we know that is we can look at the spectral signature and see that it matches. It's actually basically kind of a distorted reflection or image of a galaxy that's actually really far away and really, really directly behind that massive gravitational source. And so it's bending the light around. And that's one of the ways. Now, lensing is not new. This is not a new thing for Webb. We've been doing lensing for a while. In fact, people have even looked for evidence of exoplanets with lensing. But the point is that it's an amazing representation of the power of the Webb instruments to be able to do this and to do it so quickly, like you said. To say nothing of the broader point of the deep field images. As we heard the NASA administrator, Bill Nelson, say yesterday, the field of view we're seeing here is the equivalent as if you stand in the night sky and you in your arm, you take a grain of rice and you hold that grain of rice at arm's length. The amount of sky that's blocked by the width of that grain of rice is this area here.
It's kind of scary, to be honest, Paul.
It's almost immaterial. Right? I mean, we do not have the neurons to go and process this. But if you basically point the telescope into this very small, the reasoning being, of course, if you point the telescope anywhere in the sky with that kind of size and let it integrate for a while, then open the shutter, so to speak, and take that image, you get an image of this. This is what our reality is all around us. And some of these galaxies, we've never seen them before. If you compare them to the Hubble image, the clarity, the color, the depth just isn't there in Hubble. Again, that's not to rag on Hubble. This is what happens when you get a new generation of instruments. But we can see stuff that some of these things, now we don't have an actual specific quantitative measure for how old some of these things are yet. At least I don't know if they've published that yet. But some of these really reddish looking things are some of the oldest things we've ever seen in the universe. And one of the basic questions, of course, we have is, when did conventional galaxies in their modern shape, or the shape they have today, when did they form? What do the first generation of galaxies look like? And this is the kind of question we can start to answer with things like these deep field images.
So these galaxies that formed in the very, very early universe, they could be different. They could be lower in heavy elements, for example. They could form differently. Right? They could cluster differently.
You have all these different populations of stars, and part of that is tied to the fact that the first generation of stars were essentially just helium and hydrogen. The heavier, what astronomers call metals, and I might call oxygen or neon or carbon, not things we would normally conventionally consider metals, but in astrophysics are considered metals. That stuff comes out of nucleosynthesis, comes out and basically is produced inside supernovae. It's produced when neutron stars collide, or when a white dwarf and a neutron star collide, or when it goes into a black hole. You need these dramatic galactic cosmological events to produce these heavier elements. And since that hadn't happened yet, because there wasn't enough time for those things to occur, the first generation of galaxies is presumably going to be largely depleted in those kinds of heavier elements. What does that mean for the population of stars, for how they're distributed, for the shape of the galaxy, for the dynamics affecting it? These are the kinds of questions that you can begin to answer with things like these deep field images, because, of course, it's not just a pretty picture like this image shows here. We can target, we can focus on small little things. That looking jelly bean looking
this like little red blob, This
is a blob, right? Now, even here, we're seeing, even at the resolution of Webb, we're being challenged to resolve it.
Yeah.
But that is probably a galaxy. And that galaxy dates back to within the first about 1 billion years of the universe's history. And we can look at what's inside: hydrogen, oxygen, neon. So we know there must have been some amount of what we call nucleosynthesis, the formation of those heavier elements within stars to produce those slightly heavier elements. Now, I don't see any iron there. I don't see any of the really heavy stuff, nickel, cobalt. But certainly we're seeing evidence of fusion inside stars fusing hydrogen into helium, and then continuing to fuse down the sequence to produce things like oxygen and neon. And we know that must have happened at least 12.1 billion years ago.
And I guess we can, going forwards, track those abundances as a function of time now. That's
the goal, right? Yeah, and look to different parts of the sky as well and see is it uniform, right? We know cosmologically we have these models for how the universe is expanding.
Yeah.
We don't know for sure if it's happening uniformly, and we also don't really know what's driving it. But the point is that exactly this, we have an essentially limitless number of things we can survey.
Yeah.
So basically, we just go and look at these different parts of the sky and see what kinds of trends we see if those trends hold universally.
Yeah, some models are going to get tested, and some models are going to get changed. But that's the beauty of science.
You know, we had the first image come out about 20 hours ago. We've had these new images out maybe 3 or 4 hours now. I haven't gone to the archive to see online these preprint repositories, but I'm sure this evening there'll be the first round of papers hastily written and not copy edited or spell checked, in which we'll see new models come out to try to explain what we're seeing.
In particle physics, we call it ambulance chasing, Paul. I don't know if you have that in.
I mean, like, it's essentially what's going to happen, right? You have these people trying to get first. They went wrong, but they want to be first. But you know, already you see it on social media. People are usually trying to make sense of what they see from a scientific perspective, bringing their training and expertise to bear to work out how do we explain what we're seeing, and what's new and what's not. Amazing stuff. We've got 2 more to go. Where are we going next, Paul? Let's do Stefan's quintet.
Let's do Stefan's quintet. So Stefan's quintet is over here. So this is
just a
previous
fantastic
one.
image.
Yeah.
Right. Now, I mean, again, I don't do galactic dynamics, right? Like, my bread and butter is staring at rocks and planets and surfaces. But, you know, again, even if you aren't really focused on understanding how galaxies interact with each other, looking at how the structure, the shape of these galaxies has been distorted by gravitational interactions. You can see they have arms that shoot off in different directions. It's the structure of these that really tells you something extremely important. And actually, we've seen from Webb this morning that there are 2 sets of images they released of this quintet, or this particular small galactic cluster. Where if we look at it in different wavelengths, we can see structure that we couldn't see before. Yeah. We can even see the effect of the central, we assume to be the central black holes inside these galaxies. So again, this is just an example of how it's not just the clarity, it's not just the detail we can see or the speed at which these images can be taken, but being able to look at it with different wavelengths at those high resolutions and being able to superpose them gives us a huge amount of information on the chemistry, also on the distribution of materials within them, and the dynamics, right? It's clear that these things, certainly a few of them have undergone gravitational perturbation, and this is not a normal equilibrated shape. Something's disturbed these things. But the speed at which galaxies move and get deformed is just a little too long for, you know, it will outlast our species. Yeah. So we cannot watch this happening in real time, but we can use these observations to inform computer models that can be run in a few hours or a few days. Yeah. And it's these kinds of data that are going to be critical for understanding those models. So
because we've got so many of these things to look at now, we have a huge new rich data set where we can maybe take snapshots of, oh, this one looks kind of like this, and then a little bit later another one kind of looks like this. Can we reconstruct that kind of behavior through time in our models?
Yeah, I think that will be the goal. Absolutely. And particularly if we can work out where these things are with respect to each other, we can, you know, there is information we can have about where things are located in 3D space. Of course, when we look out into the night sky, we're looking along a radius each time, right? But we can get information. Local stars, we actually have parallax. And in fact, the New Horizons probe has been taking pictures of stars from a quite different vantage point than where Earth is, and beaming those data back, and we can actually see the stars shift against the backdrop of stars, right? The background is the celestial veil. It's pretty cool. But in this context, we can get a sense of where things are in 3D space. And then we can work out and use that as inputs into computer models to basically figure out, how do galaxies interact with each other? What does it look like when they do? How are they merged? You know, we've photographed, thanks to Hubble, plenty of examples of galaxies that merge and that collide and that pass through each other. But being able to get, as you say, more data, and particularly higher resolution, more higher fidelity data, especially if we can work out on the basis of things like color, the density of dust and gas within those galaxies, and thus the star region formations and how they get affected. Yeah. All of that becomes extremely important and extremely tractable with these new data.
Yeah, there's like when I was reading up, there's all of these sub questions underneath these things. It's not just how do galaxies form. The astronomers have all of these hundreds of questions that they want to answer. Yeah. So and obviously 100 more questions will come up after we from stuff that we never thought we would see. So the final one,
which is the whole point of science, right? Yeah. We'll never, hopefully, never answer all the questions.
Otherwise, we're out of a job. So there's always more to learn. Where are we? What have we not covered?
One left. We've got the Southern Ring Nebula.
We do have the Southern Ring Nebula. Well done. That's exactly right.
These might actually be my favorite.
Favorite in what sense?
I how it looks. Again, backing away from the science and just aesthetically, I just think it's really pretty.
Yeah. So here's a picture from Hubble, and you see a lot of. Do you want to tell us what a planetary nebula is, just so people kind of understand what we're seeing in this?
Yeah, right. So the idea basically here is that we think this is a star that is at the end of its life. Actually, we now know there's 2 stars there. And basically, as it's pushed out stellar material and gas that was surrounding it away, it produces kind of shell. It's the reason there's a different color in the middle is because there's basically radiation is ionizing the gas that's close in, it's making it kind of blue with this stretch. The stuff that's farther out is a little cooler. It's more dust and particles of rock, essentially. And this is pretty cool. And the reason it's this kind of shape, it's sort of spherical. It looks like a ring, but it's actually a shell.
Yeah.
Is because this is basically pushed out in 3D space, right? We're kind of a cross section. Because even though the colors look pretty vivid, it's still pretty tenuous, and you can see through it. So imagine it's almost like a semi-translucent bubble. We're looking in, so we can see the edges really well, right? This is what Hubble gives us.
Yeah.
Pretty useful. But then you look at what JWST is giving us, and it's absurdly good.
Yeah.
And here we got 2 different images. Now I think one on the right is more infrared than the one that's
I think it's is this? I think this is actually near cam, and I think this is MIRI.
Right. Okay. And this is another perfect example of how this is essentially the same object, but if you look at the different wavelengths of light, it looks different.
Yeah.
And then, of course, you can compare them. You can look at areas that are blue in one and red in another, and that will tell you about things like how much dust there is, what kind of compositions you're seeing. But the one on the left, that's just grab me. And if you have it, if you're able to zoom in, or if you can pull it down.
In fact, I can. I think I've got the individual image, and should be able to zoom in. So maybe
just look at the structure in it. The detail is. It looks like a human iris, and you can see these lines that are coming in. That's light from those 2 binaries in the middle, basically shining through gaps.
Yeah.
Through that diffuse
it's amazing
dust medium, right? It's essentially they're crepuscular rays, like you get light shining over mountains as sunsets on Earth. And of course, we're not just seeing through the outer part of the bubble into this cross section of the ring itself, but you can see just in the top left of that image, there's sort of a linear looking thing that seems radial. That's actually a galaxy edge on, way in the background. I mean, you could spend 2 hours looking at these images and still not see everything.
It's incredible. It really is incredible. And like I said, I think that the message that I took away from today was that, look, we're basically on the edge of a quantum shift in our understanding of the universe. We've got. I think they even looked at, with the Stefan's quintet, the velocity of gas around a black hole, the spectrum of gas around a black hole. JWST is now open for business, both in terms of how far it can look, how quickly it can integrate, all of the spectrum stuff as well. All of those kind of 4 major science goals, everything seems to be up and running and ready to go. And like you said, in the coming weeks, I think we're just going to see.
It's going to blow our socks off. But I'm thinking back to when Hubble was commissioned when I was a kid.
Yeah.
And right through to today, we're getting stunning images. It doesn't end. It doesn't stop. You don't just see one stunning image and then say, "Oh, well, that was pretty good." For example, with the planetary missions, sometimes you do, because these things tend to not last as long, and you see some amazing images. But the mission comes to an end. Hubble will eventually come to an end. So will JWST. But what I want folks to really take from this is that right now the engineers at JWST think that it has at least probably 20 years of fuel to keep its position in space where it is at L2, at the Earth L2 point. And suddenly you're kind of at the point where you're like, there could be 20, 25 years ahead of us of these images that are just opening up the universe in a way we've never seen before.
Really good. I got a final question, Paul, because I know you've got teleconferences all day, so I don't want to take up any more of your time. But two linked questions. Where do you think we should look first? I know there's a schedule now. Where would you like us to look first in terms of your work? And do you have any time on the telescope?
Okay, so for your first question, where I think they should look first, I would love to know what the Uranian moons look like. So I would point the telescope at Uranus. I've spent my 10 billion to get a picture of Uranus.
Good.
Sound.
Excellent. I like it.
But I'd love to know what the moons look like and the rings. I mean, we have Uranus pictures from Keck and from other telescopes on there in infrared. Uranus is an amazing world. It has a lot of detail in its clouds. It has banding that Saturn and Jupiter have, but it's not as clear to see in visible wavelength. Uranus has it all, has rings, has moons. I'd like to see that. I don't have any time on the telescope yet. I am way too preoccupied with a bunch of other things. But one thing that really interests me is the geology of exoworlds, of exoplanets. Yeah. And as Webb is going to, amongst its many things that will be groundbreaking, it's going to start looking for more and more Earth-sized worlds. Because as you know, we've talked about this before, one of the biggest questions we have is what makes a planet Earth-size versus what makes a planet Earth-like?
This is the most amazing image I've ever seen, by the way. The diversity of planets in. Why is it like this? Why are they so different? Why are they so weird?
And that's exactly the kind of thing that JWST is going to start helping us understand the answer to these questions. So basically try and work out, why do planets form the way they do? Why do they look the way they do? How do they end up looking the way they do? What governs where they are around their host star or where they're not? These are pretty basic questions that we have, but with Webb, we're going to be able to answer them much more capably than we were before. So personally, I want them to start pointing this thing at planets, at planetary systems where we think and suspect there are rocky worlds. Let's start measuring their atmospheres. Let's see if we can get information about their surfaces. I'll take anything I can get. But for sure, this is an exciting.
I've heard a lot of talk of pointing at TRAPPIST-1. That's what the people on stream wanted. So we'll.
I'd be happy to. But here's the thing: this thing takes data pretty quickly, right? So do TRAPPIST-1, and the next week do another star system. Do them all. Follow up every single K and K2 Kepler and K2 detection. Let's see what's out there. Now we can.
I completely agree. Paul, thank you so much for taking the time. I know you're incredibly busy at the moment. Guys, head over to Paul's Twitter, at The Planetary Guy on Twitter. It always has amazing stories, amazing images. I'm sure you're going to be breaking down a few of these things as well. We had a little bit of a meme war the other day when Biden kept us waiting for ages on the old images. So plenty of awesome, plenty of awesome stuff over there. Please head over there, check out his stuff, and you've got some exciting work coming up as well, which we're not going to talk about, but there's more to come from Paul in the near future.
We'll talk more about it in the near future.
Exactly right. Paul, absolute pleasure as ever. I will let you get off, and let's talk again soon, my friend.
My pleasure. This was great. Thank you very much. And just enjoy the hell out of these images. Roll on Thursday. We see Jupiter.
I honestly can't wait. That's going to be amazing. Yeah. I didn't even know about that because I've been
that came out an hour ago, apparently. So yeah, things are constantly changing. Such as life now.
I'm just not even going to be able to keep up. So just enjoy it. Let it wash over you, and just enjoy the images. I think that's best.
All right, mate. Good talking with you.
Take care. Catch you in a bit, buddy.
See you later.
Bye now. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.